Chapter 6, Part 1, Introduction to Nucleophilic Substitution Reactions. So let's start by dissecting this phrase, nucleophilic substitution reactions. So for a nucleophilic substitution reaction, you need two things. You need a nucleophile, and you need a species that contains both an electrophilic portion and a good leaving group. And what you're going to see in this reaction is that the nucleophile is going to attack the electrophile, which will kick out the leaving group and ultimately end up with the nucleophile substituting the position the leaving group used to be in. So notice that we've created a new bond between the nucleophile and the electrophilic species, and we have separated the leaving group. So let's define some of these words here. A nucleophile is always a Lewis base. It's an electron pair donor. A nucleophile can be negatively charged or neutral. Your stronger nucleophiles will be ones that actually have a negative charge on them. An electrophile is a Lewis acid, an electron pair acceptor. It may be positive or neutral. Also, let's take a look at these words. Nucleophile literally means nucleus loving or nucleus seeking. So it is something that is negative and seeking something positive. An electrophile is electron loving or electron seeking, although probably more accurately is electron loving, and I'm going to sit here and wait for some electrons to come to me. A leaving group is a species that takes a pair of electrons when it leaves. It is displaced by the nucleophile. And most importantly, a good leaving group can leave the molecule as something that is relatively stable. So this is going to be a weakly basic molecule or ion. So we're just going to do some examples here, and a lot of this is going to move really fast for you. We're going to go through each of these mechanisms in a lot of detail. So none of this is going to go as quickly as it is right now. I'm just trying to show you some ideas of the types of reactions that you're going to see. So in this first example here, we have methyl iodide or iodomethane and hydroxide. Hydroxide is going to be our nucleophilic species, and the carbon is electrophilic. Now, why is the carbon electrophilic? Well, iodine is highly electronegative. So we have a dipole going towards the iodine, which means we have a partial positive on the carbon and a partial negative on the iodine. So the hydroxide is able to attack the carbon, and when it does, that's going to break the bond between the carbon and the iodine will leave, taking those two electrons with it. So the result of this reaction is that our iodomethane gets turned into methanol, and we end up with an equivalent of iodide. And note that the bond between the carbon and the oxygen was formed by this lone pair that did the attacking. And we're going to see really similar things through all of these mechanisms here. So in the next one, we have methoxide and bromoethane. The ethoxide can attack the carbon that's attached to the bromine, which will have a partial positive on it. Bromine has all these lone pairs on it. It can take the electrons from that bond. And now, instead of an alkyl halide, we have an ether. And again, we have bromide. In the next example, we're going to swap out one halogen for the other. And notice that the mechanism is not changing. And then in the next reaction, we have kind of an interesting one. All of our nucleophiles so far have been negatively charged. But in this next one, our nucleophile is actually neutral, but it still has a lone pair, and it's still a pretty decent base, so it's going to be able to do a nucleophilic substitution anyway. It's going to attack the carbon and kick out iodine. Now the tricky thing here is that the nitrogen, since it was neutral, will now be positive because it used its lone pair to make a bond to carbon. And this is a good intermediate. These could be a salt together, or what is more likely to happen is that this species will be deprotonated in some next step of the reaction.